about a problem I thought was interesting. So we're going to show that all finite P groups are solvable. The way we're going to do this is by using induction twice. The first induction is going to be kind of an intermediate step that makes the final step very, very easy. So let's just start off with, let's just think about an arbitrary P group. Let's call it G with order P to the n. So we're going to find a subgroup of order P to the n minus 1 so that this subgroup has index P. What that does is it's going to make this subgroup normal and also cyclic because it has size P, which is proper. So let's do this with induction. When n equals 1, we trivially have what we want. So now suppose that any group G with order P to the n has a normal subgroup of size P to the n minus 1. Now let's induct. Consider a group H with order P to the n minus 1. It acts on itself by conjugation. And what the class formula tells us about this is that the size of H is going to be the size of its center, which is everything that commutes with everything in H, plus this the index of all the stabilizers, where X ranges over all representatives of the orbits, which in this case are the conjugacy classes. But now, we know that the index of a subgroup inside H is always going to divide the size of H. But then that tells us that each of these indexes has to be divisible by P. This is because the only way that it couldn't be divisible by P is if it was 1. But if it was 1, then H of X would be all of H. But then that would mean that X is a fixed point. So this is not possible. And so we have that each index is divisible by P. So now if we were to subtract over this sum to the side with the size of H, that left-hand side is going to be divisible by P. But then the right-hand side, which is the size of the center of H, that's also going to be divisible by P. But what that means is we can take an element in the center such that the order of this element is P. Again, because the size of the center is divisible by P, and it's a group on its own. So now, the subgroup generated by Z is normal in H because Z was in the center. Then if we look at the size of our quotient group, it's going to be P to the n because it's the size of H over the order of Z. But now by induction, it has a normal subgroup n of order P to the n minus 1. Now if we take the preimage of this normal subgroup n, we're going to get another normal subgroup with order, the order of H times the order of Z, which is going to be P to the n. So now we found a normal subgroup of H with the desired size, so we're done with this first induction. Now we can induct to show that P groups are solvable. The n equals 1 case, that's trivial, we don't have to do any work. So now let's suppose that any P group of order P to the n is solvable. And then let's create a new P group, H, with the order of H being P to the n minus 1. By our previous argument, it has a normal subgroup n with order P to the n. But then, by our most recent induction, n itself has an abelian tower, written as follows. Now we can extend this to another tower. See, we've extended the n now to H. And now this is also an abelian tower because H mod n has order P and is thus cyclic, which means that H is solvable.